There, it's there, I think. Next up is Trey Wenger, whose slides will be shown in reverse order. On the Southern H2 Region Discovery Survey. Take it away, Trey. Do you know about the lights?
Nope.
Green light means you've got 2 minutes left. 1 minute left. And then red means you're done.
Gotcha. Hello, everyone. My name is Trey Wenger. I'm from the University of Virginia. And today I'm going to tell you about something completely different than what we've heard about over the last 2 days, which is the Southern H2 Region Discovery Survey. This is a project that's going to formulate a large part of my thesis, which focuses on using H2 regions to probe the morphological and chemical structure of the Milky Way's disk. This particular project is a large collaboration of people from all around the world, many of whom are in the audience today. So I'm grateful that they could be here. So the Southern H2 Region Discovery Survey is a radio recombination line and radio continuum survey looking for new galactic H2 regions visible from the southern hemisphere. Surveys like this have been done in the past. They've been going on for several decades now. But in the last 5 or 6 years, the opportunities to discover more galactic H2 regions have increased dramatically thanks to a bunch of interesting science. For example, all-sky and galactic plane infrared surveys coming from Spitzer and WISE, and the radio continuum surveys of the galactic plane and the entire sky have allowed us to pick out an unprecedented quantity of galactic H2 region candidates. And then, of course, the most sensitive centimeter wave radio telescopes in the world, like the Green Bank Telescope and the Arecibo Telescope, have allowed us to go out and search for the radio recombination line emission from these objects. So why should you care about H2 regions in the H2 region surveys? Well, of course, H2 regions are an important component of the interstellar medium. They're important for understanding the massive star formation properties of the Milky Way. But of particular interest to me is that H2 regions can tell you a lot about the galactic structure. For any tracer of galactic structure, you need an object for which you can measure its distance or derive its distance. And if you're interested in chemical structure of the galaxy, you need an object for which you can derive its chemical properties, for example, its metallicity. Stars are the obvious tracer in the solar neighborhood, but of course you can't see stars very far through the galactic disk because of extinction. So H2 regions are the classic galactic structure tracer, especially in the radio, and that's because the massive star formation in the Milky Way is confined primarily to the spiral arms. And so the idea is that if you can find all of the galactic H2 regions, you can get an idea of where the spiral arms are and their morphological properties and so on. H2 regions, we can measure their distance, the kinematic distances, and then just based on very simple radio recombination line and radio continuum measurements, we can derive a bunch of interesting physical properties about the gas, such as the electron temperature, the metallicity, which I'll talk about a little bit later, and electron density, and so on and so forth. So our H2 region survey started about 7 years ago now with the original Green Bank Telescope H2 region discovery survey. What we did was we went to Spitzer galactic plane surveys and looked for H2 region candidates. We identified H2 region candidates based on their coincident 24 micron and 8 micron emission, and then looked for coincident 21 or 20 centimeter radio continuum emission from the VLA galactic plane survey. This turned out to be an extremely accurate way of looking for H2 regions. More than 95% of our H2 region candidates had detected radio recombination line emission, showing that they were in fact ionized gas. So we identified H2 region candidates from Spitzer, and then we went to the largest fully steerable radio telescope in the world, the NRAO 100-meter Green Bank Telescope, to look for radio recombination line emission. With the GBT and with the old spectrometer, we were able to look at 7 hydrogen radio recombination lines simultaneously at around 10 gigahertz, which means that we could integrate for less time because we could average all those radio recombination lines together. And this was an extremely successful project. We more than doubled the number of known H2 regions in the small region of the galaxy that we probed. That was only the first of our several projects. Here's a schematic, a cartoon of the galaxy showing you the extent of our different H2 region surveys. This is the sun, the galactic centers at the middle here. So originally we did the Green Bank Telescope H2 region discovery survey, which is this green wedge. And then we did a follow-up survey using the Arecibo Telescope, a little bit deeper, but less H2 region candidates. And then around 2005, we published our WISE extension of the H2 region discovery survey, where we went to WISE to pick our H2 region candidates. With Spitzer, we were limited to the galactic plane within a degree of the galactic plane. And as you know, at the outskirts of the galaxy, the galactic disk warps beyond a degree in latitude. And so in order to find H2 regions out here in the outer Scutum Centaurus arm, for example, we needed to go to WISE to pick out H2 region candidates beyond a degree of the galactic plane. And then the Southern H2 region discovery survey is going to fill in the wedge of the galaxy not visible from the Green Bank telescope. So we compiled all of the galactic H2 regions and galactic H2 region candidates into what we called the WISE catalog of galactic H2 regions. This includes the 1,000 or so known H2 regions from before we started our surveys, and then the 1,000 or so that we've discovered in the last 5 or 6 years, as well as 2,000 what we call radio loud H2 region candidates. These are H2 region candidates that look like H2 regions in the infrared and also have coincident 20 centimeter radio continuum emission. And then 4,000 so-called radio quiet H2 region candidates. These look like H2 regions in the infrared, but don't have any radio continuum associated with them. In this catalog, which is available online, you can go in there and play with the data. It's actually really cool. We have listed the kinematic distances for those H2 regions for which we can derive kinematic distances. And here I've overplotted them on top of the cartoon picture of the Milky Way. The green points here are from our WISE extension from 2015. And you can see that this was a very successful project filling in the census of galactic H2 regions in the first and second galactic quadrants, including some of the most distant H2 regions ever discovered. These are H2 regions that live in the outer Scutum Centaurus arm, or at least they have positions and velocities that are in agreement with being out in the outer Scutum Centaurus arm, which has a heliocentric distance of more than 20 kiloparsecs and a galactocentric distance of more than 16 kiloparsecs. So these things are very, very far out there. So why the motivation to doing the same experiment in the southern hemisphere? Well, it should be pretty obvious that the census of galactic H2 regions is incomplete in the southern hemisphere from that previous figure, but here's a more quantitative way to visualize it. What I'm showing here are flux density distributions for H2 regions. The blue line is the flux density distribution of known H2 regions, and the red line is a simulated population, just assuming an H2 region population in the disk ionized by a single O star. And what you see is that in the northern hemisphere, the known H2 region distribution matches extremely well with the simulated H2 region distribution, down to a completeness limit of about 30 millijanskis at 9 gigahertz. Basically, we think we found all or almost all H2 regions in the northern sky that are ionized by a single O star. In the southern hemisphere, you can see that the completeness is much, much worse. We're complete only to about 2 janskis in the fourth quadrant. So this is the motivation for doing a southern hemisphere survey. So we went to the compact array in Australia. We were awarded 200 hours on the telescope last year. We observed 142 H2 region candidate fields from the WISE catalog of H2 region candidates. On each field, we integrated between 30 minutes and an hour, and we split our observing time between the most compact antenna configuration, that's the H75 configuration, and the second most compact antenna configuration, H168. This allowed us to get over some of the confusion that we have in some of these more crowded fields. I developed a data reduction pipeline that calibrates the data, images the data with absolutely minimal user input. This made it easy to go in and kind of look at the data, get a good idea of our detections so far. We'll have to go back and look at it all a little bit more detail this summer to figure out exactly what's going on. But what we found was that of our 142 observed fields, we detected 150 H2 region candidates in radio continuum. And that's just because there were, in some of our fields, there were more than one candidate in the field. And then, just to get an idea of how many recombination lines we detected, I extracted the spectra from the center of the image, and that's what I'm showing here on the top is the recombination line spectrum from the center pixel, and the bottom is the compact array radio continuum contours on top of a WISE image. And what we found was that just using that kind of first order look at the data, we discovered 116 radio recombination lines. So we've added at least 116 new H2 regions to the census of galactic H2 regions. With the compact array, we're able to average 20 recombination lines together simultaneously, so we can actually beat down the noise pretty quickly. So the science prospect here, for me in particular, is looking at the metallicity structure of the galactic disk. This is work published in Balser et al. 2015, last year, where we used metallicities derived for H2 regions in the northern hemisphere, using observations from the Green Bank telescope, to look at how the metallicity distribution changes across the galactic disk. What we found is that the radial metallicity gradient varies significantly depending on what galactic azimuth you're looking in. So in this figure here, the sun is located at the red cross, the galactic center is in the center here, and the color scale is the metallicity interpolated between each of the points, which are the discrete measurements that we made. And so you can tell it's lumpy, it's not uniform, and the structure varies depending on what galactic azimuth you're looking at. So the idea is we want to follow up these observations and fill in the galactic disk and see if this trend continues in the southern hemisphere. So what's next? We have been awarded time to do the second part of our survey starting this summer, the second epoch of the Southern H2 Region Discovery Survey, where we hope to push our completeness limit down to about 180 millijanskis, which is what this black bar is on the histogram here. So we're not quite filling in the entire census of Southern Hemisphere H2 regions, but we're getting even closer. Maybe we'll apply for a third epoch next year, who knows. So just to summarize, H2 regions are really cool. The Southern Hemisphere's census of H2 regions is incomplete, and we are filling it in slowly but surely. Thank you.
Thanks very much. Any questions for Trey? Chris, go ahead.
Yes, I find the distribution of metallicities that you have to be very hard to understand. And I'm wondering, to what extent could that be a reflection of the fact that the galaxy has a bar means that the rotation curve is much more complex than is often assumed in analyzing data?
That's right. That's a great question. So there's a couple answers here. So the rotation curve is what we use to derive the kinematic distances, of course. And so any uncertainties in that is going to move around where these points actually live on the diagram here. And so that's something that I'm actually working on for my thesis, is folding in that uncertainties in the kinematic distances to see how this picture changes. In this paper, we kind of did a little bit of analysis to see if we move around these points, how much that changes this effect. And the effect still stays there no matter how much you change the points, but it's something we have to look into a little bit more. And I forgot to mention, but these black bars here on this graph represent the locations of the long and the short galactic bars. We thought maybe that would have some influence on the distribution that we're seeing.
My question also relates similar to what Chris had to say, that the deviation, I think, from the rotation model, from the kinematic distances, is roughly about the same as the separation of spiral arms almost. If you look at your plot, if you didn't have the guidance of the spiral arms, you probably wouldn't come up with the same spiral arms. So at some point, we have to find a much better kinematic model for the galaxy and much more detailed than we presently have.
Yeah, thank you, Ed. Tom Bania says hi, by the way. You wanted me to tell you he said hi. So that's actually something else that I'm working on my thesis. For about a few dozen of these H2 regions, we have parallax measurements from Reed now. And so we can actually compare the kinematic distances and the parallax distances. And based on the preliminary results that I've been working on, they agree to about 10-15% when we get the kinematic distance ambiguity right. When we get that wrong, everything kind of goes out the window. But yeah, that's something we need to look into a lot more.
All right, let's thank our speaker again.